Have you ever really stopped to think about how a simple vibration, just a little wiggle in the air, can turn into a song that completely changes your mood? Well, today, we're going to pull back the curtain and look at the hidden physics behind every single piece of music you've ever heard. Let's dive in.
So, here's the big question. Think about it. On one side, you've got the chaotic, messy sound of city traffic. On the other, you have a perfectly played cello. They're both just sound waves, right? So what's the one thing, the one crucial element that separates them?
Here's how we're going to break it all down. First, we'll get into the secret language of sound itself. Then, we're going to decode loudness and pitch. After that, we'll see how instruments actually tame these wild waves. And to finish it all off, you are going to get to apply this stuff yourself.
So let's get right to it. What is that core difference between just noise and actual music? Well, the answer is surprisingly simple, and it all starts with understanding what sound really is. It's just a vibration.
Yep, the difference is one single word: order. Noise is just chaotic, unpredictable, messy waveforms. Music is what happens when we take those waves and we arrange them into patterns that are repeating and intentional. At the end of the day, everything we hear is just a vibration pushing its way through the air to our ears.
Okay, so if music is just organized waves, then what are the things we're actually organizing? Well, it turns out every single sound wave has two fundamental codes hidden inside it that we can control: its loudness and its pitch.
The first code is called amplitude, and really all that means is the size of the wave. Think of it as the wave's power. You know, a tiny little ripple in a pond? That's low amplitude. A giant tsunami? That is some very high amplitude. For sound, our brains interpret amplitude as loudness. A whisper is a tiny low-amplitude wave, and a big rock concert is a massive high-amplitude wave. And we have a specific unit to measure this loudness: the decibel, or dB for short. The more decibels you have, the bigger the wave's amplitude and the louder the sound feels to us.
All right, on to the second code: pitch. Now, if amplitude is the size of the wave, pitch is all about the speed of the wave's vibration. The technical term for this is frequency. The faster the air is vibrating back and forth, the higher the pitch we hear. It's the fundamental difference between a deep bass note and a super high soprano note.
And this visual just shows it perfectly, doesn't it? Over on the left, you've got a low-pitch wave. See how it's all stretched out, kind of lazy? Those vibrations are slower, creating that deep, rumbling sound like a bass guitar. But then look at the right. A high-pitch wave is all scrunched up, super tight. The vibrations are incredibly fast and close together, and that's what gives you that high, clear sound, like a flute. The takeaway here is huge. The actual shape of the wave is what creates the sound you hear.
So we have our two codes: amplitude for how loud and frequency for how high or low. But how do we take this raw physics and actually turn it into art? Well, that, my friends, is where musical instruments come into the picture.
Now, don't get me wrong. Controlling loudness is important. But the real genius, the true magic of most instruments, is giving a musician incredibly precise and repeatable control over the pitch. They're basically just sophisticated tools for messing with the frequency of sound waves.
And what's so cool is how different instruments all solve the same problem. You've got stringed instruments, like a guitar. They change the pitch by messing with a string's length, how thick it is, or how tight it is. Then you have wind instruments, like a flute. They do it by changing the length of the column of air that's vibrating inside. Even drums can be tuned by changing the tension of the drum head. Each one is a totally unique solution to the exact same physics problem. How do you control frequency?
And now for my favorite part. We've talked theory, we've talked application. Now it's your turn to be both the physicist and the musician. We're going to apply everything we just learned and build a ridiculously simple instrument right now.
Okay, go find a small box. An empty tissue box is perfect, and a few rubber bands. Now stretch them over the open part. First, just pluck the different bands. You'll hear it right away. The thicker bands make a lower sound, and the thin ones make a higher one. That's a live demonstration of how mass affects frequency. Now, for the fun part, take one of those bands, pull it tighter, and pluck it again. You hear that? The pitch goes way up. That is tension at work.
How amazing is that? In 30 seconds? You just built a working stringed instrument and took direct physical control of sound waves' frequency. You weren't just making random noise. You were using the fundamental laws of physics to create specific, predictable pitches. You literally hacked a sound wave.
So let's just quickly recap the big ideas here. At its very core, sound is a wave.
The loudness we hear comes from its amplitude, its size. The pitch we hear comes from its frequency, its speed. And musical instruments are just these incredible tools that we've designed to give us total control over those properties, turning raw physics into pure art.
And that kind of leaves us with one last big thought. If the fundamental rules of music are built on these really elegant, simple principles of physics, it just makes you wonder, right? What incredible new instruments and what kind of beautiful new music are still out there, just waiting for someone to figure them out.